So previously we learned how to draw Lewis diagrams and we learned how to draw them for single elements, but the reason Lewis diagrams are so useful to us is because we can draw compounds. And so that's what we're going to be taking a look at today. Now, this is what we took a look at last time, is we looked at how can you go from the valence shell and the Bohr model and instead just kind of skip right to the Lewis diagram showing only the valence electrons, the electrons on the outside of the atom. And what we're going to do today is we're going to take a look at how do we actually draw this for a compound or a molecule, so something that contains more than one element. Now, you've all read the notes, and so all I'm going to be doing is working through this example and showing you how is it that we go from here into the actual drawing of the compound. And so the first step that we're going to go through is we are going to count the valence electrons. And so the way that we do this is we count the valence electrons for every individual element in the compound. So carbon has 4 valence electrons. Fluorine has 7 valence electrons. But keep in mind, there are 4 fluorines. So we're going to multiply that 7 electrons by 4. Then we're going to add this all together, and you'll find that there are 32 valence electrons in this molecule. Our next step is we're going to draw the central atom. And so the central atom we're going to draw is carbon. Now leave some space around it because you're going to fill it out with other elements. Carbon is the central atom because if you have carbon in a molecule, it is always the central atom. If you don't have carbon as the central molecule, there's a couple of ways you can do this. You can look at your electronegativity chart and go with the lowest electronegativity. I personally like to use the element that has the most unpaired electrons in its Lewis dot diagram. So to give you an example, let's say we had a molecule that has nitrogen and sulfur, and you weren't sure which one should go in the center. I would choose nitrogen because it has 3 unpaired electrons, and so it should be the central atom. Now, we figured out the central atom here is going to be carbon. The next step is to bond it to the other elements in this compound. So we have 4 fluorines, so bond it to 4 fluorines. And then what we should do is count up how many electrons we used up doing that. Remember, each bond here is 2 electrons. So we use 2, 4, 6, 8 electrons, which means we have 24 electrons remaining. So our next step is we are going to add lone pairs to all of the terminal atoms. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I've used up 24 of my electrons. I have 0 electrons left to draw. And so I've used up all my electrons, and now what we need to do is we need to make sure everything has an octet. And so what that means is each atom is surrounded by 8 electrons. So carbon has 2, 4, 6, 8. Remember, each bond is 2, so it has 8 around it. The fluorines have 2, 4, 6, 8. It also has 8. You'll notice the bond I counted for both the carbon and the fluorine. And that's because they're sharing those electrons in a covalent bond. And so you get to count it for both the fluorine and for the carbon. It's kind of like sharing a bank account. It's both of the people's money. These are both the electrons of the carbon and the fluorine. So the fluorine has 2, 4, 6, 8 electrons, and every fluorine looks exactly the same. So every fluorine has a complete octet. Since every atom has the complete octet, and we've used up our total of 32 valence electrons, we have finished a complete diagram of CF4 for our Lewis dot structure. So this is what it would look like. So let's do another example. Now, this next example that we are going to do, I would recommend use a pencil. The reason I'm recommending you use a pencil is because we need to make sure that we're able to erase some of the electrons that we're going to draw at some point. And so we've reset our steps over on the left. This time our example is going to be carbon dioxide. And so the same steps as last time. Count your valence electrons. Carbon has 4 valence electrons. Oxygen has 6 valence electrons. And there are 2 oxygens. So that's 12 valence electrons just from the oxygens alone, plus another 4 gives us 16 valence electrons. Next step is we have to draw our central atom. So that's going to be carbon again. Carbon is going to be our central atom because if carbon is in the compound, it's always the central atom. Okay? Next step, you know what, I'm going to do this until I'm going to use a marker so that you can see a little bit easier until we get a little bit further. So now we're going to connect carbon to our terminal atoms of oxygen. We're going to count up how many electrons that used. So we used up 4 electrons. We now have 12 electrons remaining. So we're going to take a look at our next step, which is we counted our electrons. Remembering bonds were 2, so that's how we got to our 12 electrons. Now we're going to add lone pairs to the terminal atoms. So now I'm definitely switching to my pencil because I know what's coming. But if I were you, I would always do Lewis diagrams forever in pencil because you end up erasing some of the work that you do at times. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. That uses up all of the electrons that we had. So it looks like we should be done, but we need to count for octets. And so if you count the oxygen, it has 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons. The oxygen is good, but the carbon has 2, 4 electrons. It definitely does not have that octet that we want. It needs to have 8. So here's the trick. We need to move 2 electrons. We don't have any extra left, but we can't steal them from the oxygen. So instead what we're going to do is let the carbon and the oxygen share those electrons. In a double bond. So now if we were to count, you go 2, 4, 6, 8. The oxygen still has 8 because remember, it gets to share those electrons. But now the carbon has 2, 4, 6. It's short by 2 electrons. So what we can do is the same thing on the other side. move those electrons from the oxygen into a bond with the carbon. And now we have completed our Lewis dot diagram for carbon dioxide. So now that we've done that, we're going to continue doing 2 more examples so we can see things that are a little bit different and understand a little bit further how to do these Lewis dot diagrams. So I'm just going to move my papers out of the way. We're going to bring something else in. And we're going to be working on H2S. So I'm going to do this again in marker so you can see it. But again, you're going to want to do this in pencil because if you ever need to erase anything, it's really much easier to do it that way. So I've reset my instructions over on the side. We're going to work through them. I'm actually going to show you 2 methods that you can use to do this. So on this side, I'm going to do what we've been doing up in the corner. On this side over here, I'm going to show you a slightly different method that I like. I actually think it's really helpful and it works every time as well. So what we can do is same thing, count up our number of valence electrons. There's 1 valence electron in hydrogen, but because there is the 2 hydrogens, we multiply by 2, and there are 6 in sulfur. If you're wondering how I'm getting these, I'm getting them from your periodic table. Remember, it's based on the column that an element is in. So sulfur is in column 16, so it has 6 valence electrons. Hydrogen in column 1, so 1 valence electron. Okay, so now that we've counted up our valence electrons, we're going to draw our central atom. Now, hydrogen, remember, can never be a central atom. It can only ever actually have 2 electrons around it. So that means it can never be a central atom. It can only ever form a single bond. So that means sulfur is going to be my central atom. And now that we know sulfur is the central atom, we need to join it with bonds to the terminal atoms, which are going to be the hydrogens. And we need to count up the number of electrons that we used while we did that. So that was 4 electrons. I guess I didn't finish adding this up, but there's 8 in total. We've used up 4. So that means there is a total of 4 electrons left. And so now what we would do is add lone pairs to terminal atoms. But hydrogen can't have an octet. It can only ever have 2 electrons surrounding it, and it already has 2 electrons surrounding it. So now we still have these 4 electrons left, and sulfur doesn't have an octet. It has 4 electrons, but they can't go around the hydrogens. So what we're going to do instead is add them to the sulfur. And that now uses up all of the electrons that I have. Sulfur now has a complete octet. And we finished drawing our molecule. Now, like I said, I was going to show you another method. And so this other method I really like. And it uses drawing the diagrams for each of the individual ones and then connecting them together. It's going to look a little sloppy because I'm going to do it in marker so you can see it well, but you should do this in pencil so you can erase. You would start with the same step. You would start by counting the valence electrons, getting that number. You then continue in the same way, draw the central atom. But this time, when I draw the central atom, what I would do is actually draw it as a Lewis dot diagram. The next thing I would do is draw my terminal atoms across from any unpaired electrons, and I would draw them as Lewis dot diagrams, making sure to line up any unpaired electrons. And then I would do the same right here. Now that I've done that, I would actually just connect unpaired electrons into a bond. And you notice I actually have the same thing. 2 hydrogens single bonded to a sulfur with 2 lone pairs on the sulfur. Now you may be looking and saying like, but this one's straight and this one's like an L shape. It doesn't actually matter. The shape right now is of no importance when we draw these. But I want to show you this with the carbon dioxide because I think it's also helpful to see it there. So I had carbon as my central atom, oxygen, and remember we want to line up our lone pairs, or our lone unpaired electrons across from unpaired electrons over there. Oxygen. And then we're going to pair up electrons to form bonds. And notice now we have these unpaired electrons here. Well, I can take this unpaired electron, and pair them up in a bond. And then take this unpaired electron and this unpaired electron and pair them up in a bond. Now where I've scribbled them out, you would erase them because you have an eraser, but I'm working in pen here, or marker here, so. But you can actually end up getting the same structure using a slightly different method. So let's do one more, and we're going to do ammonia, or NH3. So the same exact steps that we have been following all along, and I'm going to get rid of them so that we can do one without it. Count your valence electrons. 5 for nitrogen, that's from the periodic table. 1 for hydrogen, and there are 3 hydrogens for a total of 8. That's right, there's only 8 valence electrons in this molecule. So now draw your central atom. Your central atom is going to be nitrogen. Why? Because it has to be. I'm also going to switch colors because I'm running out of black. Now, draw connections to your terminal atoms. That used up 2, 4, 6 electrons. I have 2 left. I can't add them onto my terminal atoms because my terminal atoms are hydrogen. They can't accept any more electrons. So where do they go? Well, nitrogen doesn't have a complete octet yet. So 1, 2. And now nitrogen does have a complete octet, and there is my final structure. Okay, let's do this on the other side in the other way. You would still count up your valence electrons, and then you draw your central atom, and you give it its dots as a Lewis dot diagram, and then draw your terminal atoms as Lewis dot diagrams, and then connect any unpaired electrons. Same structure. And so this is how you can draw Lewis dot diagrams. The method you choose does not matter as long as you get the right structure in the end. The next thing you need to do is practice. Practice, 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 because the more you practice this, the easier it gets, and it is one of the fundamental skills when it comes to dealing with molecular geometry and understanding how molecules actually work. Okay, so please make sure you go practice, and then next we'll take a look at exceptions to the rules that I've shown you here.